Okay. Yeah. Hello, everyone. So I hope you already joined with the QR code. Okay. And so next week we will have the midterm exam. So this will be midterm, and the class will be on same class. Okay, same class. There, 511. Okay. Topics will be chapter 1 until chapter 4. So hopefully today uh, maybe I can finish most of the topics today, and next Friday I can review. Okay, I can review and maybe um, make another additional video for you so that you can also try to work out the exercise as well. Okay, I think we can start. Okay, let's start for today from the feedback. Okay. From the feedback, uh, we have the L'Hopital problem. Okay, so if you check uh, the limit, if you check the limit here, it will be infinite over 0, right? So this is indeterminate powers. And we can always solve the indeterminate powers with the ln, with the help of ln. And then you can see some L'Hopital here, L'Hopital at least 3 times until we get that this is 1. So that the answer will be e with power of 1. Okay, so don't forget to take this result 1 to the e. Okay, because I think most of you did a good job finding 1, but you need to take this 1 to e. Okay, because it's on the ln, right? So we need to have e with the power of something. So the answer is e. Okay, the next number. Okay. Next number, I think it's quite direct, straightforward. First, always check. Okay, always check the limit. It's 0 over 0, so you can do L'Hopital and derive 4 secant squared for x. Derive the bottom one, 1 plus 2 cosine 2x, and check again here. This will be 4. This will be 3. So 4 over 3. Okay. Oh, okay. So it's a direct result. Okay. I think most of you did a good job here. Okay. The third one, this is if you see the form here, it's 1 over x minus 1 over tangent inverse x. Okay, so it will be the infinite minus infinite, or this is indeterminate difference. Okay. First, we can conjugate both of these fractions, became 1. So this will be the result. It's 0 over 0. Okay, and do L'Hopital, and this is the result for the L'Hopital. Rewrite the form. Okay, rewrite the form. Simplify, and then you can see that I can cancel both of this. Okay. and then I will have the x squared tangent inverse x 1 plus x squared plus x. We check the limit, it's still 0 over 0. Okay, and we can do L'Hopital one more time. Can do L'Hopital one more time, and then check again, and then it's 0 over a constant, right? It's 0 over constant, so 0 over constant, so it's 0. I think you also did a good job here. 0 is the result. All right, now that's the L'Hopital. Now for today's class, actually we can have some examples. Okay, some examples. So first, okay, let's try to do this. Okay. Okay, so I have this question here. A rectangle has its base on x-axis, and the upper two vertices is on the parabola of y equal 4 minus x squared. What is the largest possible area of the rectangle? Okay, so I already did the picture for you. So the parabola y 4 minus x squared is the blue curve here, okay, and the rectangle is inside those parabola with the base is x-axis. Okay, so let me give you some time whether you understand what the question or not. Okay, this is still continuation of the last Friday example. So you need to find the optimizations. Okay, the optimizations. Okay. So if you look the curve and the rectangle, or if you look the rectangle, actually the rectangle can be many shapes, right? It can be like this, it can be this, right? It can be this, it can be this. Okay. Depends uh, on what will be in your final result. So it can be this, right? Or it can be this, or it can be this, right? There are several ways to draw the rectangle. We need to know what is the dimensions, right? The dimensions to make the area the largest area. Anyone find the answer? Okay, to begin with, we can just using any variable here, but I think we can just state the variable as x and y for the rectangle here. And to make it maybe clear, I will start from the first quadrant. In the first quadrant, so this will be x, and this will be y. So the area of the rectangle will be, it's 2x multiplied with y. Okay. And this will be the optimizations, right? And this y equal 4 minus x squared. This will be the restriction, right? Or it's the constraint. And then it's directly substitute, right? For the area is 2x 4 minus x squared. We can solve it uh, for the functions here. And let's say this is our models here, our models that we are going to utilize to find which one is the optimum dimensions. So we can say that this is, let me write here, A. So we need to take the derivative of these functions with respect to x. And this will be 8 minus 6x squared. And this should be equal 0. So that we need to find the critical point. So x squared will be 8 over 6. Or this is 4 over 3. Or x will be plus minus. Okay, since x is positive, we are just going to have the 2 over square root of 3. Okay, that will be the x. And y will be 4 minus the 4 over 3, 8 over 3, right? So area will be 2. This will be 32 over 3. Okay. If you want to stop here, that's okay. This is already correct. Okay, any questions? Any questions for the first problem? the first question. Okay, next example. Okay, let's try this. Okay. A cone-shaped drinking cup made from circular piece of paper, cutting out a sector and joining the edges. CACB as the picture. You can see the picture. Find the maximum capacity of the cup. So find the volume, right? The largest volume possible. I give you some help to give the variables name if you want. Let me give you a few minutes to try. The constraint is a constant. Then you need to relate the R and H. Okay. This R is a constant. Okay. Hmm? This is the constant. Okay, so the capital R is our constant. Okay. So if you read the question carefully, a cone-shaped drinking cup is made from a circular piece of a paper of radius R. So this is your paper. Okay. The R is already fixed. Okay. So it can be any number, but it is a constant, okay, for this question. And then it's cutting out the sector, and they join this ACCB, and then it's make a cup. Okay. So you have the cup, a cone-shaped cup. You can find the volume. Okay. And then this R will be your constraint. Okay. This will be your constraint. So you can relate the R, the small r, and the H with this R, with the triangle Pythagorean theorem, right? Okay, but let me write for you. So this first we can write as this, right? Okay. And our volume will be pi over 3 r squared h. Okay. Now we can say changing this into r squared minus h squared like that, okay, so that we can have 4 over 3 and we can solve this. Okay. So this will be our volume, our functions. We take the derivative with respect to h. Okay. Actually, you can choose which one you want to substitute to here, but I think it's better to substitute the r squared, right? If you substitute the r squared, it's you are going to substitute this. If you want to substitute the h, then you need to at least square root this, right? And it will be, I think, maybe complicated. So I think better this r squared. And you have the, let's say, v prime here is equal, it's pi over 3. This is r squared minus 3h squared. Okay. And this is equal 0 for our critical point. So r squared is equal 3h squared, or h squared is 1 over 3 r squared, and h will be r over square root of 3. So this will be our critical point. Okay. We take the positive one, of course. Okay. So the maximum volume will be 5 over 3. We can say r squared is So 2r cubed, 2 over 9, 2 over 9, yeah. 2 over 9 square root of 3, and then pi, the big R, and then cube. So this will be the max capacity for the maximum value. And if you, maybe for example, if you need to check whether it's a maximum or not, we can check through our zero to R. I believe this will be positive, this will be negative. And you know that, okay, it's a maximum value. Okay. Now the uh, another example that I can give you is this. Uh, Find an equations of the line. Okay. Okay. So there's a question. Why take derivative of h? Okay. Actually, you can take derivative of the small r. Okay. For example, from here we can take this into h squared, and we know that this will be this, right? You can take this and take it into here, and we can take the derivative of small r. Okay. I take the h because it seems that it will be uh, easy to solve with the derivative. Okay. If I take the derivative of h, because the volume it has the r squared, okay, and then r squared we can take this one here. We can take the big R squared minus h squared. We can substitute. We can substitute this to here, and we now have this volume equations. Okay, and remember this R is a constant, right? A constant, and we have a nicely uh, volume equation with h as a variable. So that's why I take derivative of h, and then you can have this nicely derived. Okay, that's why I take the h. You can take the small r, okay, and then you can exchange this h with this. But I think the equations become a little bit complicated with the square root, right? So that's why I take uh, the h for the derivative. Okay. Okay. Any other questions? No. Okay. From the classroom? Any questions? No. The last one here. It's okay. It's okay. Okay. The other one that is example. So finding the line equations that is through 35.35. That is cutting the least area from the first quadrant. Okay. So remember, you have a quadrant. Okay. You have 4 quadrants, right? So the first quadrant is the all positive, right? When x and y is positive. Hmm. Remember, it is the first quadrant, right? First assumptions is this line will be this or this, right? Okay, so first thing is you have an equation of line. Okay. It should through 0.35, maybe 35 here, this one here. Okay, cuts off the least area from the first quadrant. Okay, so we need to have exactly line equations. Okay, that is going through this 0.35. Okay, if we take this, okay, can we make an area from that point line? No, right? No, right? Is it this line here? But if you take the line becoming this, we are going to have an area that is precisely cut off this first quadrant. Okay, so let me draw this so that the online student can also observe. Okay, okay, let's take this 3, 3, 5. Okay, let's say that that's our line. Okay, so this will be 0.35. Okay, and what will we do next? Let's take the subject here as our variable x, okay, that we need to find. Okay, so we need to find what this point here and this point here, that when we take the area will be the minimum, okay, the minimum area. So we need to take this variable x here and variable y. That's the idea for the question. Okay. Okay. Now we have triangle. So let's just write triangle. Triangle uh, area is half x1. Okay. Because we now have the line equations, we can try to make out the slope. Okay. Because we have the at least we have the slope, okay, as maybe variables. Okay, the slope. Okay, first we can take the line equations y uh, using the uh, 0.35. Let me write that 0.35. We have y minus 5, and then have some gradient x minus 3. I need to write that the gradient should be a negative. Okay, don't forget this, because from the slope it's going down. It's negative slope. Okay, we can take this and make uh, our equations. Okay, at least we have now first equations. Why this half xy? It's the triangle area. area of triangle. Okay, this is area of triangle. Okay, what's next from the equation? We need to take this x and y, right? So this x is happen when y is 0, right? So we can take y 0 and then solve this for x. And we take this when x is 0, and we have y. Okay, let's just write that. Okay. So x and y intercept. So when x is 0, so y will be 5 minus 3m. When y is 0, then x will be, let me write one by one. Mx will be equal with y plus 3m minus 5, and x will be this is 0, sorry. 3 minus 5 over m. Now we have the equation that using variable m, right? And then remember we have the area is half xy. So we can take the x, take the y, okay, and take this multiplications. And we have 25 over 2m minus 9 over 2m. And then this will be 3 plus 15. Okay, now this is our models of our functions that we need to derive. Okay, to derive this ddm. Should be equal 0. So m squared or 25, or let me write one by one. 25 over 2m squared is equal negative 9 over 2. Oh, wait. This should be positive, this should be negative. And this should be positive. Okay, I think that's correct. Cancel that. So m squared will be 25 over 9. Let me put this on the left. Put here. This size is a bit smaller. M squared is 25 over 9. So m is plus minus 5 over 3. Okay. And we need to take the negative, right? So we take the negative because of the slope is negative. Okay. And then we can take the equations. Plus 5 plus 5, so this should be plus 10. So this will be the, this will be the equations. Now, any questions? Okay. Okay, so the idea behind these questions is most of the optimizations. Okay, first, the very first example I give you is really simple. Okay. You are given uh, the constraint and optimizations directly, but if it's not given, maybe not really direct in the questions, you need to think, okay, which one are your optimizations, okay, and which one is your constraint. So first here, if you look at the area, okay, maybe before the area, first you need to understand the question first. Okay. First, the question is saying the area when you have the least area of the cutoff of the first quadrant. Okay. So first you need to decide if this point here, and you need to cut off the first quadrant, you need to cut off from here, right? Okay. So this cut off the x and y perfectly like that. And then have a triangle. Okay. I think the best way to approach the area is just using the area of triangle. So area of triangle, half base is x and the height will be y. And another thing is you have a line equation. You can put the line equation here, and it becomes clear that this m is something that we need to find so that uh, the area can have the minimum area. Okay, and so from here we take the intercept, okay, to find the x equation, y equation here, the base and the height, and the base and the height put back through the area, okay, and eventually you will have this equations, right? You solve the equations, look at how the equations will be, and then derive the equations. Okay. And of course, when you derive this, you already have one variable, exactly one variable, m. Okay. Okay. So I think you can have more exercise, especially solving optimizations, and especially um, questions that is not really that long, okay, but it is certainly in a mathematical problem. Okay, if the questions is asking about like a functions, you have uh, like how to calculate like a profit, and then you need to take derivative and so that, and all the information already in the questions. I think it's already we have already done that. Like it's easy step by step. But questions like this and maybe the previous one, you can try to solve that kind of question because uh, we don't have quiz for this one, for the chapter 4. We will directly have the midterm. So in the midterm, because I will also include chapter 1, 2, 3, and 4, the questions will be not really heavy on like uh, chapter 4, like really long questions. Okay? So it should be short, but the way you are solving it, it should be having some analytical problem. How and you need to analyze, you need to observe, okay? And of course, if the question is asking, is uh, the m that you got is minimum or maximum, you need to know how to prove. Okay, you need to know how to prove using the line number or using the concavity. It's also okay. Okay? So if you check the second derivative from here, what will happen? Okay, Okay. And I think also maybe this week I want to upload another video, maybe 15 minutes video, maybe another maybe three example, okay, for you, okay, so you can also check. And please let me know when you uh, decide to work on the optimizations part. If you still think maybe one or two questions still difficult, not difficult, maybe stuck. Okay, if the question is difficult, like hard, but you can solve it like slowly, that's okay. If the question is you don't have any clue how to solve, please let me know. Okay, please let me know that question. Okay, that will be the optimization. And I will leave uh, most of the part, and maybe the review part also, maybe with your TA, but maybe reviewing this optimization, I think that's most important. Okay, any questions? If no, then I will have some additional notes. Okay. This is about the Newton's method. Okay. Let me write this some additional notes. Okay. Because I think I already mentioned the Newton's method before. Maybe let me give you some reminder. Okay. If you have the approximations, okay, you have linear approximation. Okay. Or if you would like to write from the very okay, we start from this linear approximation here. The linear approximations, as you may know, and in your chapter 3, we need to find uh, approximate value of the functions, right? So this will be the unknown value, right? The one that you need to compute. And usually A will be, or let me write here, A will be some value that you're already familiar with, known value. Known value for the, okay. If we are going to reverse this, okay, and uh, when the value is 0, what is the x? Okay. This is actually the questions for the Newton's method, or it can be solved through the Newton's method. So let me write the Newton's method, what it means. So when f of x 0, so let me write this is 0, and let's just take the equal, okay. Oh, let me maybe draw first. Okay, let me draw first to make it clear. Okay, let's say we start from this uh, a, or let me write a as x0. Okay. Okay, when you have x0 here, okay, and you are going to have some point at the curve, and from that point we can make a tangent line like this. Okay. I think I can make the x0 a little bit, maybe a little bit here, so that I can make a tangent line that is visible. Okay, maybe that is okay for you. We can see the tangent line is making uh, crossing over the other x value. We call this x value x1. Okay. Okay. Now from here, we can write the equations. Let me write y minus y1 x minus x1. From here, we can take the of x f of x0, okay, plus f prime x0 and x minus okay. So for this x1 here, we got this. Okay. So when f of x is 0, this is what we are going to have. Oh, sorry. It should be x1 minus x0. Okay. If you look here, okay, this is x0, okay, this is x1. Okay. Okay. Now, when we have the value of the function 0, which means at this value here, okay, this is actually, we are going to say that we have y1. Okay. This is our y and y1. We can look from this x0 and x1. So when this is 0, we have f of x0 plus f prime of x0 here at this x0, and then the delta of the x will be x1 minus x0. This delta, right? Okay. You have the tangent. Okay, this is the slope. Okay, and you can rewrite the equation and it becomes this equation. Okay. Precisely, this is our linear approximations, it's similar, okay? Or mean value theorem also similar equations. But the questions in the Newton's method, okay, we are going to have uh, the functions is 0, and we need to find the x. Okay? In the linear approximations, we know the x. We want to find the value of the functions, okay? And uh, we have a and x. Okay? X is for our unknown value. A is for the known value. Right? But in the Newton's method, we are kind of um, reverse this equation, and we need to find these terms here, this x. Okay? So that's why we have this x1 minus x0, this. Okay, and of course, okay, if our x0 is something that we are start at the beginning, okay, we are so you have a curve, the blue one here, and how to approach this curve. Okay, let's say we start from this x0 here. Okay, we are going to have our tangent line is around here. Okay, it's going to have x1 here, and it's still too far. Okay? What we are going to find is actually we are going to approach this, okay? These roots. Okay, so we are going to approach this when the f of x is 0. The x is here, right? So let me give you this notes. So this is roots. We need to find these roots. Okay, that's the idea. Okay, how to find? Of course, if you look uh, at the picture here, okay, well, you know that this is the root, right? But let's say you are not sure the picture is looking like this. Okay? Of course, you try some x, right? You try some trial and error. Okay? When we are doing that trial and error, it's actually we are going to have it's going to have this. What about if we get closer? Let's take here. It's going to have this, the tangent line. And when it is really, really close, the tangent line will also getting close to our goals, right? But the most interesting within this method is if we take this x0, we are going to have x1. We are going to use this x1 and take the tangent line. And we are going to use this x, another x, and going forward, and we are going to have a good approximation. Okay, let me deal with this. So we have another line here. And let's say we have another one. Say we have, this is x2. Okay. And if we are going to use this x2, it is going to have, it's really, really getting closer. So we have x3, let's say. So if we are doing repetitions again and again, our answer will be getting closer to what we are going to find. So if you have any complicated functions and you want to know, can you find the roots of that function, we can try this method. Okay, we can try this method. So how the methods works is, so you have x1, so you just simply put in your x0, get some results, check the results. If still maybe too far from complete 0, then try another one, x2, and this become x1, x1, x1. So you have a repetition or some iterations. Okay. And you know the error from uh, the difference, the real roots, and the x1 or x2 or x3. They will have some percentage of error. The more you get closer to zero, the error will be good. Okay, will be good enough. And also the questions can be asked. Maybe it's asking when the error, maybe some percentage, maybe 0 point something error. What is the x? Maybe that can also be the question. Okay, some additional notes for the status method. Okay, let me. Okay, any questions? Any questions? Of course, it seems it's good, right? It's good method to approach, but of course, it has also a weakness. Weakness. Let me go introduce you to the weakness of this method. Let me write the Newton's method. It works very well. Okay, so works very well if okay, the value of the f prime not small, okay, and value of the second derivative not too big. And this is the important thing. The x0, the point you start at the beginning of the method, should be starts nearby the real roots. Okay. Now, how the Newton's method fail. Okay. So first, if we take this curve, let's say we have this kind of curve, we take the x0 here, okay, maybe it's around here. If we take this, maybe not to, let me take this around here. Okay, if you see from my point of view here, if you take this as your x0, okay, it seems it's too far, and we have x1 here. It seems not going anywhere, right? So first is your x0 is too far. That's the problem. So you pick x0 is too far. Another problem that might have, okay, is okay. The first problem, the weakness is if we take the x0 too far, seems we cannot evaluate more. Okay? And if this happens, so let's say we have, let's say this is our x0 and this is our x1, the result from x0. Maybe not really clear, maybe a little bit like that. So this will be x1. If we take the x1, it goes back to this one. So sometimes, okay, you take some x0, you get the x1, you take the x1, and it goes back to where the x0 is nearby. So it became a cycle. This is also a weakness that Newton's method can have. Okay? So you can have a cycle. Okay, now that's the Newton's method, and I think Newton's method is just one of the we call numerical approach for finding the x. Okay? And as long as you know the principle of Newton's method, I think that should be okay. Okay, you find the how to find x0, and you put in your formula x1 is equal x0 minus the f x0 divided by the f prime x0. Okay. If you forget the formula, you can derive from the mean value theorem or the linear approximation because it's similar. And then you take the x as your solution. Okay. You solve for the x, and you will get the Newton's method. Definitely, you will get the Newton's method. Okay. And remember how the Newton's method fail. Okay, if you take too far, if you take and maybe becoming a cycle, that will be fail. Okay, the method will be fail. Okay. Okay. Last sections of the chapter 4. Okay, and I think I will continue this part on also on Friday, and maybe a review for the whole maybe some chapters, maybe review some exercise. Okay, maybe last year midterm or maybe last 2 year midterm. I will explain that to you. Okay, now the last part is 4.9. It's called the anti-derivative. Okay. Okay. First, before we define, okay, the we already know there will be an integral, right? So before we arrive at integral, what's the integral will be? Let's say we have, okay, if we have a function, I will write as a capital F like that, whose derivative is the function. This is a small f. Then f is called an antiderivative of f. So f, big F prime x is equal to f of x. Okay, and then if f is an antiderivative of f on an interval, then the most general form of antiderivative where C is an arbitrary constant. So if we have the, for example, if we have the f of x is x squared, then the antiderivative will be, this will be 1 over 3 x cubed plus c. Okay, remember this is before we introduce the, the integral symbols, before we introduce the integral symbols. this is from, if you have x with power of n, this will be 1 over n plus 1, x n plus 1. Okay, this is the very obvious one, the power formula, the power rule. But I think I can take to the another slides to write some obvious derivative and antiderivative. Okay. So if you have a c constant, if you have this, then the antiderivatives will be just constant and f. And if you have f of x plus g of x, this will be f of x plus g. And of course, this is just in general function terms. Okay. So this will be function and antiderivative. This is from what we have learned from chapter 3. So this is 1 over x. This is, should be an x, but you need to have the absolute value. So e to the x, e to the x. And what else? B to the power of x. This is b, x, and l and b. This is cos x, sine x, and sine x, cos x, secant x, tangent x, secant x. This is 1 over. Okay, I think this is what we have learned, all functions and derivative. Okay, the idea behind, okay, before we are moving to the integrals. So here is, we can think the antiderivative as when you look from the right and look from on your left. Okay, what we learned in chapter 3, when we have sine, we have cosine. When we have cosine, actually we have a negative sign, but this is negative cos, so that you have a positive one here. Right? So actually, this kind of method, okay, from imagine from a functions, and you need to think what is the form before the functions is derived, is actually one method of integrations that is really useful. Okay, so let me give you an example. Okay, let me give you an example here. So antiderivative. Okay, let me introduce you to this integral symbol. Okay. Actually, you can also think from the differential, if you remember, dy over dx. This is f prime x. So dy is f prime x dx, and dy, if you integrate, become the antiderivative, and this will be the let's say this is the f prime. Okay. So this will be integrations of f prime x dx, and f prime is our equal with f. So we can write this as So we can also think from differential point of view. So we have this antiderivative. We call this indefinite integral. Okay. So in integrations, okay, in integrations, we have uh, two parts. Okay, we call the intuitive definition. What we have here is our intuitive definition, the antiderivative. Antiderivative. And the other one is proof with geometric, okay, with an area, right? This will be proved by the Riemann sum. Later we will have this in chapter 5. Okay. Okay, but first we are going just to look at the antiderivative, okay, as it is the intuitive definition of the integral. So if we have integral of sine x dx, okay, which means is what is the antiderivative of sine x? We know that this will be negative cos x plus c. And of course, to make sure how we can answer this, we can write, then you can have this. Okay, it's going back to the original equation, so that's our answer is true, okay? And of course, if you have the power, x with power of n, we say that this is x n plus 1, n plus 1 plus c. Okay? And if we check our x, it becomes n plus 1, x n plus 1 minus 1. It's become x with power of n. And that's true, right? That's, okay, now if we check the 1 over x dx, integration of 1 over x dx, this will be, if we write an x plus c, we are going just to have, we derive this. Of course, we have the 1 over x, okay? But actually, remember that this should be an absolute value here, okay? So that we have it became two ways. The first one is the positive x. The second one is the negative x. So this will be 1 over negative x and negative 1. Right? And this is also 1 over x. If you remember this, okay, this is why we have the absolute value. Okay, another one that is obvious is the secant squared x dx. This is our tangent. And this will be tangent inverse x. I think from the table before, I think I will just maybe mention this 5 that is, I think, crucial. because well, I think also E, but I think E is easy to follow, right? E, you already know E would be, if you derive it's still E, if you integrate it's still E with power of x, right? Okay. Yeah, physical is the midterm exam. Physical, yes, physical exam. Okay, and then let me just take some few notes here. So if we have f prime equal g prime, then we can write this equals 0, and as a conclusions we have to have a constant. Okay, to have a constant, and we can write that f of x is g of x plus c. So we have the f and g is the antiderivative of a function, f big small big capital big capital F and capital G. Okay, so uh, yeah, let me go through just a brief intro for our geometric approach. Okay, so this is integral or integration. Okay, so the idea behind the integral is we need to find the area under the curve, in which we have the notations from the previous one, the integral f of x dx. This part here is called the differential. Okay, so if we have something here, the interval is from a to b. The first thing we can take is maybe we can take some. We slice this curve, okay, and we take this small rectangle here. So we can have a small rectangles, and we take this in a small delta x, and this is let me write here. This is our f of x. Okay. And then how many rectangles? It will be n rectangles. So the idea behind how to calculate this is we take the area of each rectangle and then plus from the interval A to B. So we have rectangle 1 plus rectangle 2 and so on after some n rectangles, and that will be the area of under curve. Okay. Okay. So this part, after this part, it will be the chapter 5. Okay, chapter 5. So I will stop here. So this integral. Okay. We will have another integral after our midterm. Okay. So for this Friday, I think I will review our course so far, and maybe giving you more time to work and have some exercise. Yeah. So don't forget, next week we have a midterm. The class should the class should be here, or if I have another announcement, I will make announcement if we have another class to have. Okay. Okay. But the time is the schedule is the same. Okay. 8 a.m. 8:10 a.m. Okay. Okay. Any questions? Any questions? Okay. If not, then we will have some feedback. Okay. Okay. I think we can start. Okay. Okay. Can I start 3, 2, 1? I hope the time is enough because this is optimizations. Okay. I give you 3 minutes, almost 4. I think should be enough. Error? What kind of error? Oh, really? Okay. I think it's asking the minimum, right? The minimum, right? Okay. And then we can check later. Okay. And the last question. The minimum vertical distance. If the answer has a decimal, you need to write in fractions. Fractions. Okay. If it is maybe 1/2, 2/3, you write 1 and /2. Okay. 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 Okay, congratulations. So that will be the end of our course. Okay. By the way, I just checked the last assignment. I forgot to check. Okay. So I think a few of you still have some problem with the derivative, and I hope you can practice well on this week, okay, to prepare a midterm. Okay. And yeah, I think that's it for today. Uh, Then if you need to have if anyone needs the QR code, this will be the QR code. If you want to take the QR code. Okay, you're welcome, bro.